This is video number 3 of the 3-part video series on electrical resistance concept. In the last 2 videos, we talked about circuits where the resistors were connected in series. Today, our focus is on the resistors that are connected in parallel. But before you watch this video, I recommend you to watch part 1 and part 2 for better understanding. For further explanation, I would use the same 2 analogies that I used for resistors in series, the water pump system and the game ride elevator. I have a circuit here that shows 3 resistors that are connected in parallel. When the current comes out of the power source, it flows through the conducting wire till it reaches a point where the current divides. Some of it flows down this branch through resistor 1, some through this branch, that is resistor 2, and some of it flows down through resistor 3. The current flowing through all these 3 branches meets back again and goes back to the source. The key point to remember here is that in a parallel circuit, the current splits and takes different routes. In other words, the current divides. So, if I is the total current flowing through the circuit, the divided current in R1, R2 and R3 will be I1 plus I2 plus I3, which will be equal to I. First, let's look at the water pump model. When the water from the lower tank is pumped up to the top, it first gets collected on the top tank. From there, it goes down through these holes. Some of it flows down through wheel 1, some through wheel 2, and some through wheel 3. Just like the current in the circuit, the water also divides into 3 paths. Now, let's quickly look into our next model, the game ride. It has only 2 floors. An elevator that can take people to the upper floor. From here, they have 3 ways to go down. Some can go down the staircase, some can go down the ladder, and some can go by sliding down the pole. We will look at the concept using both these analogies and then apply it to the circuit. In the water pump, when water from the top goes down these wheels, it loses the same amount of its potential energy no matter from which water wheel it goes down, because potential energy depends on the height. And as you can see, the height is the same for all the water wheels. Similarly, in the game ride model, when people go down from top floor, they all lose the same amount of energy, no matter which path they take. Why? Because the height between the 2 floors is the same for each of these paths. Now, if we apply this concept to the circuit, the electrical potential energy supplied by the battery will be same for all the resistors. When the current flows in the circuit, which is nothing but flow of charge, the same amount of electrical potential energy will be lost in each resistor. The amount of electrical potential energy is voltage. While going through the resistors, the voltage will be dropped or lost, and it will be the same in all the 3 resistors, that is R1, R2 and R3. So what is the key takeaway here? When resistors are connected in parallel, voltage provided by the battery is the same as the voltage drop across all the resistors, that is R1, R2 and R3. So voltage drop for R1 will be V1, for voltage drop in R2 will be V2, and for R3 it will be V3, and all these will be equal to V. That is, V1 will be equal to V2, which will be equal to V3, and all these 3 will be equal to V. Now it's time to do the derivation. For resistors in parallel, as I said in the beginning, the current in the circuit divides. So the total current I flowing in the circuit is I equal to I1 plus I2 plus I3. Now, you remember Ohm's law? it's V is equal to IR. So I will be equal to V divided by R. Therefore, for resistor R1, current I1 will be V1 over R1. For R2, it will be V2 over R2. For R3, it will be V3 over R3. By plugging all this information in the equation, for total current we get V over R is equal to V1 over R1 plus V2 over R2 plus V3 over R3. Since now we know for resistors in parallel connection, the voltage is same for all resistors. It can be cancelled out. So we will be left with 1 over R equals 1 over R1 plus 1 over R2 plus 1 over R3. Rearranging the above equation, we get R equal 1 over R1 plus 1 over R2 plus 1 over R3. This is the formula for total resistance in parallel. However, it's easy to calculate by using 1 over R equals 1 over R1 plus 1 over R2 plus 1 over R3, and later you can take its reciprocal. And always remember, this equation can be applied for n numbers of resistors in parallel. And now it's time to solve some problems. But before solving, it is always a good idea to draw the diagram and write down all the information that has been provided in the question. So now that you have seen the question and the diagram is already drawn, so it's time to solve it. So just look into the information what has been provided here. This is a circuit in parallel with 3 resistors R1, R2, R3 that's connected in parallel. R1 is 6 ohm resistor, R2 is 4 ohms and R3 is 3 ohms. I is the total amount of current which is coming out from the battery, and I1, I2 and I3 are the current that is being divided in these 3 resistors. Alright, so as we already know the formula to find total resistance in parallel, which will be 1 over RT. T stands for total resistance, which will be equal to 1 over R1 plus 1 over R2 plus 1 over R3. Okay, and now we'll just plug in the values. So 1 over RT will be equal to 1 over R1 is 6 ohms plus R2 is 4 ohms plus R3 is 3 ohms. If we calculate this, we get 1 over RT equals 2 over 12 plus 4 over 12 plus 3 over 12, which is equal to 2 plus 4 plus 3 is 9 over 12. Okay, if we take the reciprocal of this number, we get 12 over 9. And if we calculate it, it comes to approximately 1.33. And the unit for resistance, as you know, is ohms. So this is the total resistance is 1.33 ohm. Total resistance of these 3 resistors. Resistor 1, resistor 2 and resistor 3. Okay. Now that I have solved this problem, I have a challenge for you. Can you solve this question? I hope these videos helped you to understand the concept of resistors connected in series and in parallel.